Okay, so pushing on with our lecture material in week 4, we want to look at modulation. So what actually is modulation and what are we going to be learning in this series of slides? So after we study these slides, we want to understand what modulation is and the role that it plays in network communications. So modulation essentially allows us to communicate an information signal across a network within the physical constraints of that channel. So we have carrier waves, and on those carrier waves we want to include our information that we want to communicate. So these signals are modulated onto the carrier wave within the constraints of the channel. Okay, so the constraints may exist in terms of the bandwidth, the frequency, for example.
In order to convey the information.
So there's a number of different types of modulation that may be applied. The pulse amplitude modulation and the pulse code modulation and their application to analog signals. And then we have amplitude shift keying, frequency shift keying and phase shift keying in relation to modulation of digital signals.
And this is a method of
and then we want to calculate the modulation index and the modulation depth. So we want to understand how we can understand how we can determine the extent of modulation which has been applied in each scenario. Okay, so the modulation index and the modulation depth are very similar attributes. The depth builds on the index, but they both reveal the extent to which the signal has been modulated.
Is a technique where
so to begin modulation, we're thinking about the carrier wave. So the carrier wave is a waveform that is modulated with an input signal for the purpose of conveying information. So the carrier wave is that wave which is being communicated across the channel, and we want to add our information to this carrier wave in order to pass the data to the receiver side of the network. The carrier wave is usually a higher frequency than the input signal. So our input signal is modulated on top of the carrier wave. The higher frequency gives it scope to accept our information for transmission and to be able to carry the information that we wish to communicate.
Transmits data by varying the amplitudes.
The purpose of this carrier is to transmit the information through space as a wave, as an electromagnetic wave, or it's to allow several carriers at different frequencies to share a common physical transmission medium by frequency division multiplexing. So by using different frequencies, we can communicate multiple streams of information simultaneously. So it's how we want to use that communication channel in order to convey this information. So as an example of the frequency modulation, we have our carrier wave, which is an existence between the communicating devices, so the sender and the receiver.
Sequences of pulses for
we have our signal of information here, the data that we actually wish to communicate.
So the logical way
and
is
we can apply our signal on top of the carrier wave, modulate the carrier wave so that our information is represented on this wave, and by doing so convey that information to the receiver. So we have here an example of frequency modulation. So frequency refers to the number of cycles per second of a signal.
Square pulse to transmit this
so
data.
How often does the signal go through its full cycle? Frequency, remember, is measured in hertz, and 1 hertz equals 1 cycle per second. So we're adapting the number of cycles per second in order to convey our information.
The voltage or the amplitude
where we wish to communicate a binary 1, for example, we're modulating this frequency
is actually
in order to represent this information that's being communicated. Similarly, when we're conveying a binary 0, again, we're not actually modulating this signal here. The frequency is not changing from the carrier wave, and in doing so and keeping that state the same, we're representing a binary 0 as being communicated.
We're only using 8 pulse amplitudes for
so the signals that we use in the real world,
so we're
such
using
as voices, are analog signals. So why exactly do we need to use and apply modulation? So So the
These
signals
8
that we're trying to
amplitudes
communicate are
can be
analog signals.
represented using a 3-bit
Analog
code.
transmission occurs when the signal sent over the
So we
transmission
can
medium
represent
continuously varies from one
each
state to
of
another
the
in a
8 signal
wave-like
levels
pattern.
using a 3-bit
So we have a
code.
continuous wave of information of
So after
values
quantizing,
which are
samples
trying
are
to be communicated
taken at specific
throughout
points
the duration
to
of
produce
an interaction
amplitude
between
modulated
devices.
pulses. So we've got our
Okay, so
amplitude
telephone
modulated
networks, for
pulses
example,
here.
were
And
originally
these are
built for human
represented
speech rather than
using
data.
3
So it's
binary digits.
this speech, this continuous data
As we've
stream,
used only 8
which is present in the
levels,
analog
we
waves.
need 3 binary positions to hold
In
each
order to
pulse.
process these signals in computers, we need to convert the signals to a
So if we're
digital form. So we've
digitizing a
talked
voice
about
signal,
this quite a
there'll
lot
be 8,000
throughout the
samples
course of
taken
this
per
module.
second.
So
And
when
these
we're
8,000
converting the
samples
signals
are
to a
then
digital
transmitted
form,
as a stream of
we
zeros
want
and
to
ones.
transmit our electrical
So
pulses
8,000
in
samples
the form
times 3
of
bits per
binary
sample
digits 1 and
would
0.
require 24,000
Okay, so
bits
these are
per second
baseband
transmission
signals.
rate.
A baseband signal
In
is typically a
reality,
signal which
we
has
have
a very
8 bits per
narrow
sample
frequency range.
and the 8,000
Okay,
samples per second
they can be transmitted
actually
without
require
any modulation, so
64,000
without any
bits per
shift in the
bits
range
per
of
second
frequencies of the
transmission rate.
signal and are of low
Okay,
frequency.
so this is how we
So they're
think
contained
about
within the
converting
band
this signal
of
into
frequencies
a
from
digital
close
signal
to
for
0 Hz
communication.
up to a higher
Okay,
cutoff
so we've got a
frequency or
series of
maximum
levels,
bandwidth.
and
So
with
it's
each
this low
level
range of
we
frequencies
have
which
a
are
certain bit
communicated
code which
in a
represents
baseband signal.
the value at each level.
So why use modulation? So if we consider a channel essentially acts like a band pass
Okay,
filter.
so
Okay, so
this
a band
information
pass
is
filter
communicated using
is
a
one
square
in
wave,
which frequencies within
and
a
there'll be
certain
a
range are
trade-off
allowed
when we're
through,
using the
but
square
other
wave
frequencies
in
outside of that
relation to the
range
wide
are actually
bandwidth,
rejected.
because
Okay,
the
so
high
if we
frequency
consider a
components of this
channel that
wave will be
essentially acts
attenuated by
like
the
a
channel, so they'll be
a band
weakened by
pass
the channel.
filter,
The
both the
strength
lowest
of the
frequency
signal will be
components and
reduced,
the highest
and
frequency
the
components
waveform will
are
then be
unusable
prone to more error
in some
on the
way,
other end
and
of
transmission is
the
only
communication channel.
practical over an
But
intermediate
the
frequency
number of
range.
possible
So
pulse
if we can
amplitudes can
shift
be
the low
infinite
frequency
within this
signals
scheme,
up,
but it's usually
then we're
some
going to
power of
result
2,
in some
so that
loss
the
of the
resulting
data that we
output
wish to
can be
communicate.
digital,
So the
binary
modulation
1
allows
and
us to
0.
shift our signal frequency and to fulfill a more successful communication.
So to summarise the pulse
So
amplitude
modulation allows us to
scheme,
send a signal
we
over
have
a bandpass
data being
frequency range.
transmitted, which is
So within
encoded
a
in the
certain
amplitude
acceptable
of a
frequency
series
range,
of signal
we're allowed
pulses.
to communicate once modulation has been applied. If every signal gets
this
its
is
own
one
frequency
approach to
range, then we can
digitising our
transmit multiple
analog
signals
signal.
at the same time over
It
a
is,
single
however, a
channel
rarely
using
used
different
technology
frequency
today,
ranges.
and it's been
So in
superseded
doing
by
so,
other
we're able
techniques
to
such as
maximise the
pulse
efficiency
code modulation.
of the
So
communication.
we'll go on to
We're
look at
being able
pulse
to
code
maximise the
modulation in a bit more
utilisation
detail.
of the channel capacity. So it allows for more efficient communications to take place. So in addition to being represented by an analog signal, information can also be represented by digital signals. So we have our binary ones and zeros here, which are representing positive and zero voltages. As we've seen in our signal level slides, a signal can have more than 2 levels. So we can encode multiple bits of information for each level, and thereby increasing the effective capacity of the communication channel. So just as a reminder, we've seen how we can have a digital signal with 2 levels, or we can have a digital signal with 4 levels. So where we have our 2 levels, where we have a positive value here, we have the transmission of a binary 1. Where we have our 0 value here, we have the transmission of a binary value 0. Where we have our digital signal with 4 levels, for each level, we're actually communicating 2 bits of data. Okay, so we're transmitting more information within the same ability of the network, the same signal level of the network. So we send 1 bit per level in the first figure, and we send 2 bits per level in the second figure. So if we have a signal with a certain number of levels, each level needs a certain number of bits in order to represent that data which is being communicated. So if in our example we have a signal which has 8 levels, we need 3 bits of data in order to represent the information which is being communicated. So here's the question now. So in a communication scenario where we have a digital signal with these levels, how many bits are needed per level? And we can work that out to be 3. Okay. So to think about some terms, whenever we're talking about modulated signals, we can think about both the bit rate and the baud rate. So these are 2 terms which you may come across whenever we talk about modulating signals and the transmission of information. So many data communications over networks occur via serial data transmission. So serial data transmission refers to sending data 1 bit at a time. Okay, so the speed of this data is expressed in terms of bits per second, and the data rate is a function of the duration of the bit or bit time. Okay, so the rate at which that data is transferred. So the rate can also be called the channel capacity. Okay, and is measured in bits per second, megabits per second, and so on. So to compare the bit rate with the baud rate refers to the number of signal or symbol changes that occur per second. So how many shifts in that signal level that occur per second. Okay, so a symbol is one of several voltage, frequency, or phase changes of our signal. So the bit rate and the symbol rate or the baud rate are only the same when 1 bit is sent on each symbol, so on each level. When we've got 1 bit being sent on each level, the bit rate and the baud rate will be the same. So to compare the bit rate versus the baud rate, bit rates measure the number of data bits, 0s and 1s, transmitted in 1 second in a communications channel. So if we're transmitting 2,400 bits per second, this means that we're transmitting 2,400 0s or 1s per second. The baud rate is the number of times a signal in a communication channel changes state. Okay, so a 2,400 baud rate means that the channel can change state up to 2,400 times per second. Okay, so this term changing state refers to it changing from a 0 to a 1 or from a 1 to a 0 up to 2,400 times per second in this example. So there's different encoding techniques, different modulation techniques which may be applied, and there's a number of different reasons why each may be applied in different scenarios. So we may be working, for example, with digital data, digital signals, can be working with analog data and digital signals, digital data and analog signals, and analog data and analog signals. So there's a relevant modulation technique for each scenario in order to convert the signal into a form which will best be represented on the communication channel. So in the case of digital data and digital signals, for example, the equipment is less complex and expensive than digital to analog modulation equipment. Okay, so the data will be transmitted in a digital way using the digital signals. In another example, we're transmitting analog data using analog signals. Analog data in an electrical form can be transmitted easily and cheaply, and this is necessary whenever we're working with voice transmissions. Okay, so there's a number of different reasons why each type of encoding of modulation may be used depending on the physical channel and perhaps the application which is being communicated. So we want to convert the signal from the continuous time domain to a discrete time domain. We use the process of sampling. Okay, so whenever we're working within the context of this module, we're thinking about the conversion of continuous waves to digital waves. And we do this using the sampling, which we saw in week 3, and then the quantization, which we saw in earlier set of slides this week as well.
So we sample that signal and we want to digitize that signal in order that it may be communicated across the constraints, within the constraints of the physical channel which is available to us. So we need to take into account the fact that there are constraints and certain characteristics of the channel which need to be accommodated. So any transmission system has a limited range of frequencies, and this restricts the data rate that can be carried. So we need to ensure that our signal can be communicated within an effective spectrum and an effective bandwidth. And that will influence the way in which our signal is converted prior to communication.